When we have a single variable function, and if we enlarge the function at a specific point, and we can see that the function will resemble to a line, and we call that the tangent line. Similarly, for a multivariable function, for example, a function of two variables, if we plot that on an xyz coordinate system, then we get to a surface. And if we enlarge the surface at a specific point, we can see that the surface will resemble to a plane. And we'll call that the tangent plane. In this lecture, we are going to find the equation of tangent plane for a function of two variables. Here it shows a surface that represents a function of two variables. And we want to find the equation of the tangent plane at this point. And suppose it has coordinates of x0, y0, and z0. Then using what we learned from lecture 49, an equation of plane that passes through x0, y0, and z0, the form of the equation would be some constant a times x minus x0, then plus constant b times y minus y0, and plus constant c times c minus c0, and this equation equals to 0. Then that's the general form of an equation of plane that passes through the point x0, y0, and z0. And the constants in this equation, a, b, and c, are the components of the normal vector of the plane. Now let's do some simplification. So I want to write the z on one side. So I'm going to let another constant, a, be the negative of first component of the normal vector divided by the third component of the normal vector, and another constant, b, as the negative of the second component of the normal vector divided by the third component of the normal vector. Then if I substitute this, then I can rewrite this equation of plane as c minus c0 equals the a that I just defined times x minus x0, then plus b times y minus y0. And let's call this equation 1. Let's revisit the graph again. The intersection of the tangent plane, which is this yellow plane, with the plane y equals to y0, is basically the tangent line T1 for the curve C1 at point P. And if I substitute y equals to y0 into equation 1, then my equation 1 becomes c minus c0 equals a times x minus x0, because the second term will vanish. And now this equation only has two variables, x and c. And this form is an equation of a line, where the line has slope of a. But from what we just noted from the graph, we know that the intersection line is T1. And we've also learned from the interpretation of partial derivatives, T1 is also the partial derivative of the function with respect to x at the point x0 and y0. So I can rewrite the slope a as the partial derivative of the function with respect to x at the point x0 and y0. Similarly, if I look at the intersection of the tangent plane at P with the plane x equals to x0, then from the graph, you can see that the line is T2, which is the tangent line of the curve C2 at point P. And from the interpretation of partial derivative, slope of T2 also equals to the partial derivative of the function with respect to y at the point x0 and y0. So we can also rewrite the constant b as the partial derivative of y at the point x0 and y0. Then if we substitute these two equations back to our equation 1, then I get to my equation of the tangent plane. So suppose f has a continuous partial derivatives, then the equation of the tangent plane to the surface f of x and y at the point x0, y0, and z0 is this equation here, c minus c0, and this part is the constant a that we define, which equals to the partial derivative of the function with respect to x at the point x0 and y0, then times x minus x0 plus the constant b which is the partial derivative of f with respect to y at x0 and y0, then times y minus y0. Let's look at this example. Let's find the tangent plane to the elliptic paraboloid c equals to 2 times x squared plus y squared at the point 1, 1, and 3. So using the equation that we just derived, we will need the partial derivative of the function with respect to x and y at point 1 and 1. So let's let a function of two variables, f of x and y, be 2x squared plus y squared. Then, the partial derivative of the function, first with respect to x, that would be 4 times x, and the partial derivative with respect to y, it would be 2 times y. Then if I substitute the point 1 and 1, for the first function, it equals to 4. And for the second partial derivative, if I substitute 1 and 1, it equals to 2. Then I simply need to substitute these two values, 4 and 2, into the equation that we just found. So we can write out the equation of the tangent plane of this surface at the point 1, 1, and 3 is c minus c0, where c0 is 3, equals the partial derivative with respect to x at 1 and 1, which is 4, then times x minus x0, where x0 is 1. Then plus the partial derivative of f with respect to y at point 1 and 1, which is 2, then times y minus y0, where y0 is 1. And now we get to an equation of the plane. Or, we can simplify this equation and rewrite the equation of the tangent plane as c equals 4 times x plus 2 times y and minus 3. The figure below shows the surface f of x and y, also the tangent plane at the point 1, 1, and 3. In panel A, we can see the shape of the surface and the tangent plane at this point 1, 1, and 3. Then in panel B and C, we start to enlarge the surface. So you can note from the x and the y axis, it was -4 to 4, and now we enlarge to -2 to 2. So we see that the surface starts to resemble to a flat plane. And if we enlarge even more, in panel C, now the axis is from 0 to 2, we see that the surface resembles to the tangent plane. And that will actually relate to the next lecture. So in the next lecture, we are going to use the tangent plane to do a linear approximation.